In 1843, a guy got so excited about a math idea that he vandalized a bridge with a pocketknife. His name was William Rowan Hamilton. He was out on a walk in Dublin with his wife along a canal, and the thing he'd been chasing for 10 years just landed in his head all at once. He didn't have paper, so he pulled out a knife and cut the formula into the stone of Broom Bridge. Here's what he scratched in. I squared equals j squared equals k squared equals ijk equals -1. That's it. That's the whole thing he'd been stuck on for a decade, and it fit on a bridge. And honestly, the first time I read this story, I thought it was one of those math legends that gets prettier every time somebody retells it. But the bridge is real. There's a plaque on it now, and people still walk out there to see the spot. So the obvious question is, what could possibly be worth carving into public property? What are these things? To get why he cared, you have to know what he was actually after. Hamilton loved the complex numbers. You've maybe seen these. You take the real number line, and you add one new number called I, where I squared is -1. And the magic is that this isn't just algebra, it's geometry. Every complex number is a point on a flat plane, and multiplying by them rotates and scales that plane. So multiplication became motion. You could spin a two-dimensional world just by multiplying numbers. Hamilton thought that was gorgeous, and I'm with him. But he wanted the next floor up. We don't live on a flat plane. We live in 3 dimensions. So he wanted a number system that would do the same trick for 3D space. Multiply 2 of these new numbers and rotate the world you're standing in. Sounds reasonable. It ate 10 years of his life. So here's the natural guess, and it's the one Hamilton made too. Complex numbers have one real part and one imaginary part. To reach 3 dimensions, just add another imaginary direction. Call it J. Now every number looks like a plus BI plus CJ. 3 coordinates, 3-dimensional space. Beautiful. Adding these is easy, no problem there. But the moment you try to multiply 2 of them, you hit a wall. You end up needing to know what I times J is. And it has to be some combination of 1, I, and J, because that's all you've got. Every single option Hamilton tried either broke a rule he cared about or collapsed back down into something two-dimensional. He would wake up, his kids would ask him at breakfast, "Dad, can you multiply triples yet?" And he'd have to say, "No, not yet," for years. Imagine that being the family bit. Let me actually show you the wall, because it's a good wall. Say you decide I times J has to be something. The cleanest guess is that I times J equals J times I. Just like normal numbers, order doesn't matter. That feels non-negotiable. 3 times 5 is 5 times 3. Why would this be different? But watch what happens. If you assume that, and you also want lengths to multiply nicely, which he did, the algebra forces I times J to be a plain real number. And once I times J is just a real number, your fancy new direction folds back into the plane. You're stuck in 2 dimensions again. So Hamilton kept the assumption that order doesn't matter, because giving it up felt insane. And that assumption was quietly strangling the whole project. I got this wrong the first time I worked through it. I kept insisting order should be safe. It is not safe. Okay, the walk on the bridge. The idea that hit Hamilton was 2 things at once. First, stop trying to do it with 3 coordinates. Use 4, 1 real part and 3 imaginary directions, I, J, and K, which sounds like cheating, like he just gave up and added a spare. But hold that thought. Second, and this is the real heresy, throw out the rule that order doesn't matter. Let I times J not equal J times I. In fact, let I times J equal K, but let J times I equal -K. Same 2 things multiplied in the other order, and you get the opposite answer. That's the move everyone had been too comfortable to make. Multiplication, where a times B is not B times A. We call that non-commutative, which is an ugly word for a simple idea. The order you do things in changes the result. Before you decide non-commutative is some weird abstract nonsense, look at your own hands, or really any object near you. Grab your phone. Do this. Turn it 90 degrees, so it's face up but rotated flat on the desk. Then flip it away from you so it's standing up. Remember where the screen points. Now start over, and do the same 2 turns in the other order. Flip it up first, then rotate. It ends up facing a completely different way. Same 2 rotations, different order, different result. Rotations in 3 dimensions genuinely do not commute. This is not a math trick, it's a fact about space that your hands already know. So when Hamilton said his multiplication has to be non-commutative, he wasn't breaking math to be edgy. He was finally matching the math to how rotating things in 3D actually behaves. The old rule was the thing that was wrong. Let's actually pin down the rules, because they're weirdly clean once you see them. We have I, j, k. Each one squared gives -1, just like I did in the complex numbers. And they cycle. I times j is k, j times k is I, k times I is j. Go around that little loop the forward way, and you always get the next one, positive. Now go backward. J times I, k times j, I times k. Each of those gives you the negative. It's like a circle with a direction painted on it. Forward is positive, against the arrow is negative. That single carved line on the bridge, ijk equals -1, secretly contains this whole table. You can derive every product from it. I think that's the part that got him. 10 years of dead ends compressed into one loop and one equation you could teach a kid. Now back to that nagging thing. Why 4 numbers to describe 3-dimensional space? It feels like one too many. Here's the way it finally clicked for me. A quaternion isn't a point in space. It's an instruction. It's a rotation. And to fully describe a rotation in 3D, you need to say 2 things. Which axis are you spinning around? That's a direction. 3 numbers worth. And how much are you spinning? That's an angle. 1 more number. 3 plus 1 is 4. The extra coordinate was never a spare part. The real part carries the angle, and the ijk part carries the axis. So a quaternion is a little machine that says, tilt your head this way, by this much. The 3 imaginary directions point the axis. The real number sets the amount. 4 numbers, because a rotation is genuinely a 4-number thing. Let me show you the actual trick they do, at least the shape of it, without drowning you in algebra. Say you have a point in space you want to rotate. You dress it up as a quaternion with no real part, just the ijk coordinates. Then you take your rotation quaternion q and you sandwich the point between q on one side and its inverse on the other, q point q inverse. And out the other end comes your point, rotated exactly. The sandwich is the whole idea. And here's a genuinely strange bonus. To rotate all the way around a full 360 degrees, the quaternion only has to go halfway. It takes 2 full trips of the object to bring the quaternion back to where it started. This is the same weird double cover thing that shows up in electrons and spin. Quaternions were quietly hiding a piece of quantum mechanics a century early. That still bugs me in a good way. So you'd think everyone threw a party. They did not. A lot of mathematicians and physicists of the era looked at quaternions and recoiled. The extra dimension bugged people. The non-commutative thing bugged people even more. Lord Kelvin, a huge deal at the time, straight up called quaternions an unmixed evil to those who touched them. That's a real quote. He was not being playful. There was basically a decades-long feud between the quaternion people and a rival crew who wanted to split the useful parts off into something simpler. That rival approach became modern vector algebra, the dot products and cross products you meet in school. The cross product is literally the leftover imaginary part of quaternion multiplication, cut out and served on its own. So the thing that supposedly killed quaternions was made out of quaternion parts. Math history is pettier than you'd expect. Here's the plot twist that makes this fun. Quaternions were supposedly dead for most of the 20th century, a beautiful antique. And then computers showed up, and specifically anything that had to rotate a 3D object smoothly and reliably. Video games, flight software, robotics, the Mars rovers, the spacecraft that has to know which way it's pointing. If you rotate things the naive way with a stack of angles, you eventually hit a nightmare called gimbal lock, where 2 of your rotation axes line up and you lose a degree of freedom and your object jams or flips out. Quaternions just don't have that failure. They interpolate between orientations cleanly. They don't drift, they're compact. So the exact objects a Victorian genius carved into a bridge, that the smart money called evil, are now running quietly inside basically every device that knows which way it's facing. Hamilton was just 150 years early, so the little carving on Broom Bridge won. The knife scratches wore off the stone ages ago, by the way. There's just a plaque there now. But the idea outlived the man, the feud, and the century that dismissed it. Let me leave you with the thread that still gets me. Hamilton spent 10 years assuming that a times B has to equal B times A because it always had. The breakthrough was giving up a rule that felt like it couldn't possibly be optional, And once he did, it turned out the universe had been non-commutative the whole time, in your hands, in electron spin, in how any object turns in space. The rule we clung to was the local weirdness. So here's what I keep chewing on. What's the A times B equals B times A in your head right now? The obvious thing you'd never think to question, because Hamilton's whole discovery was on the other side of one of those.